Hello everyone, and welcome at the 19th episode of Science News. Today we'll be looking at a paper published in Crystal Growth and Design that's principally coming from Malaya University in Thailand, led by the group of David J. Harding and other collaborators around the world. This paper is a look at how structures of iron complexes affect their properties in terms of their spin crossover. But before we dive into the paper itself, let's just have a little look at where spin crossover is coming from and what it is. Spin crossover, or the origin of spin crossover, comes from the properties of complexes of transition metals that have electron configurations between D4 and D7. Here is a diagram of the d orbitals for such metals for the case of having 5 electrons, and essentially depending on the structure of such complexes, depending on the central metal and its ligands, there are two principal ways in which the electrons in this case can be distributed in the T2G and EG sets of the orbitals. On the left is the high spin state, where those 5 electrons, as I mentioned, are distributed one each in each of the 5 orbitals. And on the right we have the low spin situation. As you can see, that it appears where the energy difference between those two sets of orbitals is larger, where all 5 orbitals are in the lower T2G set of orbitals. And what essentially spin crossover is about the fact that in certain structures, depending on the conditions, the complexes, the structures can change from being low spin to being high spin, or from high spin to being low spin, depending on properties, depending on the conditions. Here I can see that one way to affect this change of going from low spin to high spin and vice versa can be temperatures. This also has an implications to the properties of the complexes, to the structures. The structural features such as bond lengths, bond angles do change as a result of transferring from one spin state to another. And importantly, from the point of view of applications, it's the magnetic properties of the complexes do change as well as a result of the transition from low spin to high spin. And spin crossover materials do have various potential applications, such as in information storage, actuators, or sensing, and that's why they're attracting significant amount of interest from researchers. And one thing that people have learned, and that's also one of the focuses of this study, is the fact that it's not just the complex, or the metal and its ligands that are important in terms of designing materials that perform well in terms of their spin crossover properties, but it's also, for example, in the case of cationic complexes, the counter ions, the anions that are there with the cationic portion of the complex, can have an effect on the spin crossover properties, or it can be metals from which these materials, solvents from which these materials have been obtained, that also can have drastic effects on the properties of whether the materials exhibit spin crossover or not, as we can see over here, where materials based on the same iron complex, depending on on the alcohol from which they are crystallized either exhibit or don't exhibit spin or crossover properties. And so that brings us now to the work in this particular paper, which is focused on iron 3 complexes of the ligand shown here. It's a ligand based on 2-naphthol, with the 2-naphthol being decorated with further 2 nitrogen binding atoms. And this then binds in a 2-to-1 fashion with iron 3 cation and forming a cationic complex, which is then complemented and charge complemented by halide anions. In the case of this study, the halide anions investigated were chloride and bromide. Further variation of properties were achieved then by crystallizing the complexes of both anions from 3 different solvent systems: dichloromethane hexane, chloroform hexane, and 1,2-dichloroethene hexane. The first system gave hexane solvates, the second solvent for both of the complexes with the 2 anions. In the case of the second solvent system, complex 1 gave a mixed solvate where both chloroform and hexane are involved in the material, whereas complex 2 gave solvate with chloroform only, and the third solvent system gave complexes that didn't include any solvents in the crystals, crystalline materials. So here you have some structures shown for the first solvate. So for the hexane solvates obtained from the first solvent system. In this case, the crystals, the asymmetric unit of the crystals contains 2 independent iron centers, and then makes further supramolecular arrangements, in this case into chiral helical chains. It's interesting that for when the structure of this the complexes 1 and 2 are studied at various temperatures. For complex 1, so for the chloride complex, at 150 K, both irons in the asymmetric unit are low spin. Then at 263 degrees Kelvin, one of them becomes high spin, and at 340 degrees Kelvin, one is high spin, the other is mostly high spin. On the other hand, for complex 2 with bromide anion, we start at one being low spin, one high spin at 150 degrees, at 270 degrees, one being low spin, the other one being high spin, 350 degrees, one being mostly high spin, the other one being high spin. So showing you the effect of the anions on the structure. So these the assignments here are made based on the changes in the structure as the temperature is increased. When we go to this second system, so the system which was crystallized out of chloroform and hexane, both the one with the chloride, so complex 1, and complex 2 with bromide, both of them show low spin at 150 or 200 degrees Celsius, and then at 280 at then room temperature. Equally, the system that was crystallized out of dichloroethane hexane solvent system, which doesn't have any solvent included in the crystals, doesn't show any spin crossover based on the structural investigation. What the image here shows us something that was observed for the other structures and not mentioned here, that clearly in the structures the interactions between the ligands around the metal and the counter ions are different for the chloride and bromide, which then leads to different packings and different supramolecular arrangements in the crystals. Finally, for the hexane solvent, an investigation of magnetic susceptibility by squid measurement was carried out, and as we can see here, spin crossover properties are observed by this magnetic measurement as well, with a hysteresis loop being shown. This hysteresis loop is likely due to loss of some of the part of the hexane solvent, because the structures as they were measured do not support this hysteresis loop there. Finally, in solution, the magnetic properties were measured using nuclear magnetic resonance, and once again these measurements show the switch from mainly low spin states at lower temperature to high spin states, or more prevalent high spin state for the complexes at higher temperatures. So this was an interesting study into the spin crossover properties of iron 3 complexes, once again showing how it's not only the metal and its ligands that are important for the spin crossover properties, but also the counter ions and solvents, and then these effects can be used to modulate and design the desired properties. Thank you for watching, and see you again next time.